Welcome to the talk Total Deep Variation for Linear Inverse Problems. Typically, various problems in computer vision can be cast as inverse problems. The variational approach amounts to computing its solutions by minimizing an energy composed of a data fidelity term and a regularizer. Classically handcrafted regularizers are used, which are commonly outperformed by state-of-the-art deep learning approaches. In this work, we combine the variational formulation of inverse problems with deep learning by introducing the data-driven, general-purpose, total deep variation regularizer. On the right, the proposed TDV regularizer is depicted, which assigns to each pixel an energy value. In its core, a convolutional neural network extracts local features on multiple scales and in successive blocks. This combination allows for a rigorous mathematical analysis, including an optimal control formulation of the training problem, and leads to state-of-the-art results for numerous imaging tasks.
In detail, we consider the data fidelity term measuring the quadratic distance of AX given the observation Z, where A is a task-dependent linear operator. In addition, we denote by theta the parameters of TDV. We minimize the energy using a gradient flow emanating from the corrupted input image on a finite time horizon for stopping time t. Here, the terminal state coincides with the output image. A reparametrization of the time yields an equivalent gradient flow on the time interval 0, 1. Then, t and theta are computed by solving an optimal control problem using a smooth loss and n training samples, in which the state equation coincides with the reparametrized gradient flow. Finally, we have proven the existence of minimizers for this sampled optimal control problem. Next, we derive a time-discrete version of the aforementioned sampled optimal control problem. Therefore, we advocate a semi-implicit time discretization of the gradient flow, where the fixed depth S reflects the number of iteration steps. Note that this scheme is equivalent to proximal gradient, which enables an efficient computation for many tasks. This time discretization naturally results in a time-discrete sampled optimal control problem for computing t and theta. Here, the terminal state xi is the output image. For this optimal control problem, we prove that the optimal stopping time fulfills a computable condition involving the adjoint states.
Next, we illustrate the broad applicability of our approach. First, we consider Gaussian image denoising with noise level 25, in which A is the identity operator. On the left, the PSNR curve along the gradient flow trajectory is depicted. The associated images are shown on the right. The worst PSNR value is obtained at the initial value of the gradient flow, which coincides with the noisy observation. Then, the PSNR value gradually increases until the optimal stopping time is reached. Beyond this, the PSNR value decreases and the images are oversmoothed and details are lost. Our approach can also be applied to undersampled CT reconstruction. Here, we just have to modify the linear operator, which in this case is the undersampled Radon transform. We emphasize that the used TDV regularizer is solely trained for Gaussian image denoising on natural images and not on any medical images. That is why an additional balance parameter lambda is introduced. In the same fashion, we can apply the same TDV regularizer without any modification to accelerated multi-coil MRI reconstruction and only need to adapt the linear operator. A visual comparison reveals that the resulting reconstruction is nearly indistinguishable from the fully sampled target.
To get an intuition of the local behavior of TDV, we perform a nonlinear eigenfunction analysis. More precisely, starting from an image x0, we are seeking for local minimizers of TDV that are norm-preserving. As you can see in the video, cartoon-like structures are generated and energy-minimizing patterns are prolongated. Finally, we present results for single-image super-resolution with a scale factor of 2 and 4, where A is the bicubic interpolation operator. Our approach significantly sharpens the edges and generates realistic output images, which are close to the targets. Sounds interesting? Then don't forget to check out our paper and also have a look at our code on GitHub.